document screen. The technology used in the process will be discussed in the video, which I will show you later. As you can see in the figure, there are three main components that's used in this process: the tank, the pump, and the valve, and three sensors, two temperature transmitter, and one pressure gauge. And the first one is the tank. Note that the differential of the volume is equal to the cross area of the tank times the differential of the height. It is also equal to the flow in minus flow out. And this uh, and so in Lavi software, I created this simulation subsystem for the tank, and this Q in minus Q out, and this gain is actually the one divided by the cross area, and the result will be integrated to get the height or the level of the tank. And we also have some threshold to simulate the low and high limit switch. For example, for the balance tank, we have the flow in from the water inlet, raw mill inlet, or from the circulator or the diverter, and the feed pump is set at the outlet of the balance tank. And for the pump, which control a process value, uh, the output of the P&ID controller is in the PLC is an analog signal will be transferred to the variable frequency drive, the VFD, to control the speed of the pump. And the speed of the pump will affect to the flow rate in the pipe by this equation. Q is the flow rate is equal to the velocity times the cross area of the pipe. And I assume that this second order transfer function is for the pump, and the CV control variable is the output of the PID from the PLC in the range from 0 to 50 Hz. We'll change the flow rate from 0 to maximum 12.5 cubic meter per hour. The same concept is due for the valve, except the transfer function is the first order type. And for the valve, we control the open duty of the valve percentage instead of the speed like the pump. And for the sensor, the temperature of regeneration heating section are categorized into three cases. If there is no liquid in the pipe, the temperature transmitter will indicate the ambient temperature, about 25 to 30 Celsius degree. If there is liquid but heat exchanging does not happen, then the transmitter will indicate the initial value of the liquid temperature. For the first one is the about 60, and the heating temperature is cooled down a little bit, around 58. Whenever there is heat exchanging, the temperature will indicate increase to the set point. And how about the pressure? The pressure is controlled by a booster pump speed. The faster the pump is, the higher the pressure can get. And the limitation of the pressure depends on the working pressure point of the homogenizer. And as you can see in this figure, at this point, the pressure is higher than the set point. Let's say it's the 5 bar. The speed of the pump will decrease, hence the flow rate will decrease. And the next part I want to talk about is the object-oriented programming method. Why I use this method? Based on the working principle and the technologies used in the process, there are many devices work the same ways. So object-oriented programming is logical in this case, and it can short the programming time. The first object is model. It is used for the device which work depend on a conditional signal, such as the tank level or the limit switch. For example, if the filling tank is in a high level, the bottle conveyor will run, and when the sensor detects that there is bottle at the filling position, then the conveyor stops. And this is the SCADA faceplate to control or monitor the device. Here is the numeric input that the operator can change the operating mode of the device. Mode 1 is for the automatic mode, and mode 2 is manual, which operator can start and stop the device immediately. And This light are used to indicate the device is running or stopping or being tripped. And the second one is the P&ID motor. The difference between these two functions is the P&ID controller. The controller will uh, compare the set point to the process value. This is the process value, and it will compute the output signal, the control variable here, and it will change the speed of the pump or the open duty of the valve. An operator can change the PID parameter online to optimize the response of the device. And this is an alarm page. Alarms warn runtime operator about the process condition that could potentially cause problem, and trend provide data trending and report capabilities that enable operator to quickly troubleshoot the issues and identify cost-saving opportunity. And this is the video. Before pasteurizing the milk, we need to fill the process with water. This is called circulation. That's why we open this water inlet valve. And till we get to our set point, and especially this pressure. In this process, we have a vacuum deaerator here to eliminate the air in the milk to optimize the process of heat treatment. And the air also may cause the cavitation in the pump, and it will harm the operating of the pump. And this holding tank, it is designated to hold the milk in a specified time to completely kill all the bacteria. And this is a high pressure homogenizer. Uh, there are many valves and pistons in this device which will press the product to homogenize the fat and the milk together, because there is always fat in the milk, and the fat may be curdled at the cooling section, and it will stuck the pipeline and raise the pressure in the light and will damage to the process. And this machine will work at a fixed flow rate and pressure condition, which depends on the process capacity. That's why we need to control the pressure here. And in circulation stage, we don't need the homogenizer, so we switch this valve to this position to bypass the homogenizer. And the diverter will divert the product back to the balance tank till the temperature is greater than 90 Celsius degree. But in circulation, we don't need to switch that to the diverter position, because we already have the circulator. It will drive the milk back to the drive the liquid back to the balance tank. And to supply the heat source for the heating section, we have this heat exchanger. On this side, we supply the hot steam, and on this side, we will circulate water. And this is the buffer tank to store pasteurized milk before being transferred to the filling section. And we also have a light to indicate that if we had an emergency situation, we can reset on the parameter that we have changed to the default parameter, follow the requirement from the customer. And you can see that all of this device already work at the automatic mode. Let's see the mode 1. And I think we already get to our set point. So the circulation is done. We can change the mode of the operating mode of the device if we want to change this to menu mode. To start it, we can start and stop it immediately. We can change the set point. Let's say I want this work at a 4.5 bars. Okay, let's see. Move to the filling section. In this page, I simulate the filling section. We have a bottle detector. It's essential to determine that if there is bottle at the filling position, and this will detect the level of the bottle when we fill the milk inside. And we can change the number of bottles in one box and how many box we want to produce a day. And this for the counting of bottle and box. The limitation of this simulation is the update time between the PLC and SCADA and log view. They are not synchronous, so sometimes there's lagging